So the first thing is we have our first test on Monday. So exam 1 is Monday, I guess that would be the 16th. And we still haven't covered that much material, so I mean, it should be pretty easy to figure out, what to get ready for. The topics are going to be just everything up through number 3 on, well, let's just really say 2 and 3. You don't have to worry about number 1. So numbers 2 and 3 on 1D particle kinematics. So there's going to be unit conversion, scientific notation, prefixes, and then problems like those two. And those two problems are the ones where you have, some physical locations, and it says the object goes from this location to this one in 5 seconds and back to here, So those are the kind of problems you should get ready for. If anybody has any homework questions, I'd be happy to answer those, go through any homework problems. Yeah. That's right. So the lab stuff is self-contained, although there will be some sort of crossover, but when there is, you'll see it on the practice problems too. So the exams are always going to be based on the practice problems. Yes. It's going to be just like the practice problems, and in fact, those problems go back and forth between being practice problems and exam problems and stuff. So that's a really good, gives you a good idea of what to expect. There won't be any short answer questions. That's just on the quizzes. So you don't have to, you don't have to cram to try to remember stuff from the notes or anything for this. Does anybody have any homework questions you'd like to see? Yeah.
I have one question on number 3.
Yeah.
That we were looking at when we were doing the average velocity. Right at the bottom of the equation, it was 5 seconds minus 1 second. I noticed on your solution, you came up with 3 seconds.
That's really bad subtracting.
Okay.
Yeah. Okay.
Sure if you
but
count that second.
No.
Because there was that 1 second.
No, that's just. Usually I get subtraction right, but sometimes it's still.
Okay. Cool. So that was
okay. Yes.
Cool.
Okay. Well, let me make up a problem of that type, and I'll give you some time to work on it together and stuff, and just make sure everyone's on the same page. I mean, it's really the only physics question type that's going to be on the exam. Okay, so let's say that there's a cliff here and water below. And let's say there's an especially dangerous rock here 20 feet below the top. And then from that rock, it's 30 feet down to the water. And here's the bungee jumper. Temporarily not so sure about this. Like, oh yeah, they say there's this bungee, but why they make me wear a bathing suit? And so what happens is the person jumps, and it takes 1 second to get down to the height of that rock. So I'm going to label these. I'm going to call this position A, position B, and position C. So it takes 1 second to get to B. And then it takes half a second to get to C. And then the bungee, so he just like touches his head to the water, and then the bungee catches and pulls him back up to B. And let's say it takes 1 second to get back to B. And then 1 more second to get down to C. And then at that point, the bungee ride operator starts to pull him up, and it takes, let's say, 5 seconds to get pulled back to A. Yeah, that is good pull. So first, let's do this with the 0 position at B. And the positive direction up. And for time, let's say that 0 time is at the instant the person jumps. And we want to draw a position versus time graph. Okay, so take a few minutes, see if you can figure this problem out. Talk to each other about it, as you go through it, compare steps with each other. And if you get stuck, ask me. And after pretty much everybody's done working their way through it, I'll go through it and you can compare your answer to mine. So I think, the easiest way to do this, some people might find this aesthetically unappealing, but is just to go through the steps the way like I've done them in the examples before. Just always do the steps the same, draw a little diagram of the motion, label your little diagram, translate it into a table of time and position values, and then plot those points. So I'm all for doing things in a way that's aesthetically appealing to yourself, but if you're just looking for a way to make the fewest mistakes, that's probably the way to do it, So the motion looks like this. I'm going to simplify the motion into just a line, and the motion happens along this path. And so we have the points A, B, and C at the bottom. And we know that the distances here, this is not negotiable. This doesn't have anything to do with our choices. It's 20 feet between those 2 points, and it's 30 feet between those 2 points. And the other thing that we don't control as the people doing these calculations is that the person jumps from here. At the next sort of checkpoint, they arrive here 1 second later. They arrive at C half a second after that. Then it takes 1 second to get back up to B. And then it takes 1 second to fall back down to C. And at that point, the client's head is hanging in the water, and the operator astutely realizes that letting them hang underwater is bad for business and pulls them back up to here. Ooh, it's symmetric. And this last leg takes 5 seconds. Okay, so none of that has anything to do with any of the choices about positive direction, zero position, zero time. But now we're going to start to label this stuff. I think I said that for part A, and actually I'm going to just save this for myself for later, for part B, because this is the stuff that doesn't change based on the choices. So I'm going to use this for this part of the problem. I'm going to use it for the next one too. Okay. All right, so we're going to choose B to be the zero position. So whenever the person is at B, they're at position 0. And the positive direction is up. Okay, so if you start at 0 and you go 20 feet in the positive direction, what's the position at A? Yep, that's positive 20. And if you start at 0 and go 30 feet in the negative direction, what's the position of C? Negative 30, yep. And then we're also told that at the start of the motion, did I tell you this? Maybe not. Well, dang it. I guess, so we don't know anything about when the stopwatch starts. I think there might be some practice problems like that too. We'll just, so you can make your own choice about that. I'm going to choose 0 time to be when the person jumps. Oh, I did. Yay. Okay. So 1 second after 0, what does the stopwatch say? Yeah, 1 second. 0.5 after that, 1.5 seconds. 1 second after that, 2.5 seconds. 1 second after that, 3.5 seconds. And then 5 seconds after that, it ends at 8.5 seconds. And now all we're doing is reading off the pairs, the coordinate pairs of time and position at each location. So at time 0, the position is positive 20. And that's feet. At time 1 second, the position is 0. At time 1.5 seconds, the position is negative 30. At time 2.5 seconds, the position is 0 again. At time 3.5 seconds, the position is negative 30. And then at 8.5 seconds, the position is positive 20. Any questions about any of those? And once you get into a table like this, all you're doing is just plotting points on a graph. Let's see. So our position is vertical. Our time is horizontal. The times that matter to us are 0 seconds, 1 second, 1.5 seconds, 2.5, 3.5, and 8.5 out there somewhere. And then the positions that matter are positive 20 feet and negative 30 feet. So the first point is 0 time positive 20 position. Then time 1 second, position 0. Then time 1.5 seconds, position negative 30. Then time 2.5 seconds, position 0. Then time 3.5 seconds, position negative 30. And then time 8.5 seconds, position positive 20. And so it looks something like this. Okay. In reality, we haven't talked about this yet, but maybe it makes sort of some kind of sense to you. It's impossible to have velocities change instantaneously like that. Like, for example, well, at any of these points, but especially like at here you can really see it. It has a negative velocity, and all of a sudden, without any difference in time, it has a positive velocity. That would correspond to an infinite acceleration. And accelerations, we're going to see later, correspond to forces. So you'd have to apply an infinite force to something to make that happen. Obviously, that's not possible. But we don't know any details. So all I'm saying is, in reality, this graph would be sort of rounded everywhere, you know, and go through those points. We don't know those kind of details, so this is fine for now. Okay, so now for part B, let's say that the 0 position is at the point C at the water. The positive direction is down. And the 0 time is 2 seconds before the person jumps. So do the same thing again, draw the position versus time graph. And we'll just do the same thing again, just take some time, work on it, compare answers, and then I'll go through it after you have some time. Okay, so for this one, I'm going to start out with the same just picture of the motion that I used before. This is all the stuff that doesn't have anything to do with the choices of the physics guy. So the first choice we made for part B was the 0 position was at C. So whenever you're at C, you're at position 0. And then the positive direction was down. Okay, so that means that anything up is negative. So if you start at 0 and go 30 feet in the negative direction, what's the position at B? Yep, negative 30 at B. And then if you're at negative 30 and you go another 20 feet in the negative direction, what's your position at A? Yep, negative 50. Any questions about that? And then for the time, 0 time happens 2 seconds before the motion starts. So the stopwatch says 2 seconds when the person finally jumps. 1 second later is 3 seconds. Half a second later is 3.5 seconds. Then 1 second later is 4.5 seconds. 5.5 seconds. And 10.5. So on the left, I'm going to put the times. On the right, I'm going to put the positions. The first time that we know about is 2 seconds. And the position at that instant is negative 50 feet. The next time is 3 seconds. And that corresponds to negative 30 feet. Then 3.5 seconds. And that's 0. Then 4.5 seconds. And that's negative 30 again. 5.5 seconds is 0. And the last one is 10.5 seconds. And the position there is negative 50. And now we're just plotting these points. Everything position-wise is 0 or negative, so I'm going to give a lot of room for the negative axis, but position versus time. The times that we care about are 2 seconds, 3 seconds, 3.5, 4.5, 5.5, and then 10.5. And the positions that show up are 0, negative 30, and negative 50. And plotting those points, at 2 seconds, we have negative 50. At 3 seconds, we have negative 30. At 3.5 seconds, we have 0. At 4.5, we have negative 30. 5.5, 0. And then 10.5, we're back to negative 50. Connect these points, and it looks something like this. Okay, so now, I mean, that's the end of this problem. That's all I asked you to do. But let's think about interpreting this graph like the way we are doing in land this week, and the way we started to do talking about average velocity and instantaneous velocity. Remember, the instantaneous velocity is given by the slope, okay? If slope is positive, it means at that instant the thing is moving in the positive direction, and if it's negative, it means it's moving in the negative direction. And the absolute value of the velocity, so the absolute value of the slope, gives you the speed. Okay? So what are the intervals where the person, the object that you're looking at in this, is going in the positive direction? What are the time intervals? Yes, that's one of them, and then the other one is just from 2 seconds to 3.5, right? And then there's 2 intervals where it's going in the negative direction. Okay, so then the person's going in the negative direction from 3.5 to whatever, 5.5 to 10.5. And then, can you tell from this graph where the person is moving, let's say, the fastest? When is the speed the greatest? 3 to 3.5. Yeah, Right, 3 to 3.5 is when the speed is the highest because the person is covering a distance of 30 feet in only half a second. Okay, and visually you can tell that that's the fastest because that's where the slope is the farthest from zero. Okay, that's where it's the steepest, either positive or negative. Okay, and then the slowest the person is moving over this time interval is from 5.5 to 10.5 because that person's going a total distance of 50 feet over 5 seconds. Okay, does it make sense that the person is going in intuitively now? So the person jumps off the thing, goes down, back up. Does it make sense that the person is going in the positive direction from the instant that the person jumps to hitting the water the first time? Okay, at first thought, that might not seem like it makes that much sense because on the graph, it looks like something up is happening, right? But in graph world, this thing that looks like up just means positive. And we decided before we started doing the math on this that positive was going to mean down. Okay, so anything that's any motion in the positive direction means down. Okay, that's sort of a confusing thing to get used to, I think, for a lot of people. But what this is saying is, since the person's going in the positive direction from here to here, the person's going down from here to here. And the person's going down again from here to here. Okay, so let's look at the other one. So this time, the person's moving in the negative direction from 0 to 2 seconds. 0 to, what is it? Yeah, that's 1.5 seconds. So on the graph, it looks like the direction has changed. And it's still the same motion, so we know the direction didn't change. But remember that in this case, what we chose as positive was up. So now the fact that the person's moving in the negative direction from here to here means moving down just like it did in the graph below. Okay. So that's the kind of thing that we're just sort of trying to little by little get comfortable with. So there's something that really happens. We're talking about the exact same motion, and the person really goes down. There's no denying, there's no math that can change the fact that the person's going down. But how that motion connects to math world is dependent on our choices of zero position and positive direction and zero time. Okay. Any questions about that before I go on? All right. So last time I was talking about velocity. And I did this in two pieces. I first defined the average velocity. And then I used the idea of average velocity to define the instantaneous velocity. And I said, besides being used to define instantaneous velocity, average velocity isn't going to be very useful. This is the one that we care about. And that, because of that, anytime in this class that I talk about velocity, I'm talking about instantaneous. And if I want to talk about average velocity, I have to say that specifically. And we talked about how instantaneous velocity is represented on a position versus time graph as the slope at an instant. And you can think of the instantaneous velocity of being the combination of two things. A sign that tells you what direction you're going, and the magnitude, the absolute value, which tells you the instantaneous speed. So now we're going on to acceleration. And just like velocity is a measure of change in position, so just like velocity measures change in position, acceleration measures change in velocity. Okay, well, if the relationship between velocity and position is similar to the relationship between acceleration and velocity, if somebody said you have to come up with an equation for acceleration, a definition of acceleration, you can't watch TV till you do that. Okay, so you'd cry for a while, and then you'd be like, okay, well, I just got to do this, and you go back to your notes and you look at the definition of velocity. Average velocity is the only one that I gave a mathematical definition for. And it said you take the position at the later instant minus the position at the earlier, divided by later time versus minus earlier time. You say, like, well, just put velocities in place of positions. And that's what it is. So good job. Okay, you can watch TV again tonight. So acceleration is defined as the velocity at the later instant minus the velocity at the earlier instant divided by the later time minus the earlier time. And so remember when we talked about velocity, the formula like this represented average velocity, and then we had this sort of complicated way to connect that to instantaneous. We don't have to worry about that with acceleration. It would be possible to differentiate between average and instantaneous acceleration in the same way that we did before. But all of the problems that we're going to deal with have constant acceleration. And so average and instantaneous are the same if the acceleration doesn't change. So for us, acceleration will be constant so the average acceleration is equal to the instantaneous acceleration. And we're just going to call that acceleration A. Now, there's some important things to remember in order to make sense out of what acceleration is. So notice. The first one is if the acceleration is 0, that's the same thing as the velocity not changing. Since acceleration measures changes in velocity, if the velocity stays constant, that's the same as 0 acceleration. So constant velocity and 0 acceleration mean the same thing. And in 1D, the only way you can have acceleration is if the speed is changing. In everyday language, we talk about it as acceleration and deceleration. We're not going to talk about it that way here. Everything's just acceleration. Okay. But what do the signs of acceleration mean? So with velocity, it was pretty easy to interpret. If you have a positive velocity, it means the thing is moving in the positive direction. Negative velocity means moving in the negative direction. And so you might think that positive acceleration maybe means that the thing is speeding up, and negative acceleration means it's slowing down. But it's not that simple with acceleration. So to figure out based on the signs of, the signs of these quantities, whether something's speeding up or slowing down, you have to consider the signs of the velocity and the acceleration. If the velocity and the acceleration have the same sign, then that means that the object is speeding up. And if they have opposite signs, that means it's slowing down. What about if the velocity is 0 at that instant and it, then the acceleration is positive or negative? Well, you can't slow down anymore from 0 velocity. So whatever the acceleration is, it's speeding up in that direction. Okay. Like at the first instant when you start to accelerate from rest, you have 0 velocity and you're speeding up in whatever direction the acceleration, the sign of the acceleration is. Okay, let me show an example of this. So let's say that you have a car that's moving this direction and speeding up. So it's going this way and it's speeding up. Well, we can't put signs on velocity and acceleration until we choose a positive direction. So let's say we choose our positive direction to be this way. Then the car is moving in the positive direction. So the velocity is positive. And it's speeding up, so the acceleration has to be the same direction as the velocity. So we have a positive acceleration. And then, let's see, what about the same case? But this time we choose the positive direction to be this way. Well, now the positive direction is opposite the direction it's moving, right? I mean, we haven't changed the actual motion of the car by switching the positive direction. So the car is moving in the negative direction, and that means velocity is negative. And since still physically the car is speeding up, we know that the acceleration has to have the same sign as the velocity, and so we also have a negative acceleration. Any questions about that right now?
So we could also, if we didn't have the equation speeding up and down, we just have the velocity we can figure out.
If you have the velocity and the acceleration signs, yeah, you can figure it out. And yeah, that's the kind of stuff that we're doing in lab this week too. All right, and the last thing I have to say is units of acceleration. The units of acceleration always have to be length over time squared. And that means that in SI units, the units of acceleration are meters per second squared. By the way, one way you can think of that is like meters per second. And so what that acceleration means is if you have an acceleration of 2 meters per second squared, you can think of that as 2 meters per second, which says if you start at rest, the next second, the thing will be going 2 meters per second. A second later than that, it'll be going 4 meters per second. A second later than that, 6 meters per second. So just sort of like an intuitive way to understand how that works. You know what I mean? Like this is saying whatever the acceleration is in meters per second squared, that's saying each second, how much faster are you going? Or how much slower are you going if the acceleration and velocity are opposite signs? We talked about what the instantaneous velocity represents on a position versus time graph. So now on a position versus time graph, let's figure out how you spot acceleration. Remember, if the velocity is constant, the acceleration is 0. Okay, so what would a constant velocity look like on a position versus time graph? What? Yes, not necessarily horizontal, but it would be a straight line because the slope would stay constant as time goes by. So on a position versus time graph, non-zero acceleration appears as a curve positive acceleration corresponds to a concave up curve. And negative acceleration corresponds to concave down. When I first learned about this stuff in a math class, or first talked about this stuff significantly, like a lot in a math class, it was in college, and I had this really scary, like Slovak professor with a thick accent, and the way he taught us this, he's like, concave up is like cup, concave down is like frown. So that's how I still remember it. Okay, so let's think about how this stuff would appear on a position versus time graph. So let's say we have this graph. Position is always on the vertical. Time is always on the horizontal. And let's say the motion starts like that, then does that. Okay. Are there any places on this graph where you would say the velocity is constant? Yeah, so maybe like from here to somewhere around here, it's a straight line. And so that means constant velocity, which is equivalent to saying zero acceleration. Is the object moving in the positive or negative direction over that stretch? Positive, yep, because the slope is positive. And then what can we say from about that dot to this next dot? What about the velocity? Is the thing moving in the positive or negative direction along that stretch? Yeah, it's still a positive velocity because wherever you draw a tangent line, here it's pretty, as you get close to this dot, it's pretty close to horizontal. But anywhere between those two dots, the tangent line has a positive slope. Here, and it's getting close to zero there. What about the acceleration? Is the acceleration positive or negative between those 2 points? Negative because it's concave down, okay? Because it's like frown. So the acceleration is negative. So over that stretch, is the object speeding up or slowing down? Slowing down because the sign of velocity and acceleration are opposite. What about at this point? What can we say about the velocity at that point? Yeah, I mean, it's sort of open interpretation, I suppose, but the idea is supposed to be that at that point, a tangent line is perfectly horizontal. And so if the tangent is horizontal, then the velocity is zero. So that just at that instant, the thing is not moving. So the velocity is equal to zero there. And then from that point until the end of the graph that I drew, what would you say about the velocity? It's positive. So anywhere in there that you draw a tangent line, the slope is positive. And what about the sign of the acceleration? Yep, so that's a positive acceleration because it's concave up. And since velocity and acceleration have the same sign, is it speeding up or slowing down? Speeding up, yep. Another way you can think of speeding up or slowing down is think about the slowest the thing can be is zero speed, right? To stop. And so the slowest something can be is a tangent line that's horizontal, okay? And so anytime you're getting farther away from horizontal, either positive or negative, you're speeding up. And anytime you're getting closer to horizontal, you're slowing down, okay? I like to think about it with the signs. I think that's a little easier to, a little quicker to interpret. But so for example, this one where we already figured out it's slowing down, it has a steep positive slope and it's getting less and less steep until you get there. So so that means it's slowing down. It's getting closer to stopped. Okay, and over here it's stopped at the beginning, and then it's getting more and more positive, so it's speeding up. And things like that, where you have multiple ways to think about it and come to the same conclusion, is sort of a nice way to sanity check your answers. Like, wait, am I thinking about this right? And then you think like, yeah, it's getting closer to stop here. Those, the two ways of doing it agree, so you feel pretty good about your interpretation. By the way, what does this graph mean? What does that position versus time mean? That means no motion at all, because if you think of this as, you know, a position, like say that's 5 meters, it's saying that time's going by and the object is just sitting there at that location 5 meters. Okay. So now finally we're getting to the equations that are going to let us calculate stuff. And we're only going to do calculations for constant acceleration. So I'm going to list these 3 equations for 1D particle kinematics. With constant acceleration. So these equations would not work for a case where the acceleration is changing over time. And let's say that P sub I and V sub I mean the object's position and velocity when time is equal to 0. And P final, P sub F and V sub F mean position and velocity when time is equal to time final. Then these 3 equations are V final is equal to V initial plus A times time final. The second one says P final is equal to P initial plus V initial times time final plus 1/2 A times time final squared. And the last one says 2 times A times the quantity P final minus P initial is equal to V final squared minus V initial squared. Okay, so I'm going to start with an example of how these get used, and then I think that'll be it for today. But at the start of the next class, not on Monday because we have the test, but next Wednesday, I'll give a set of steps that you can just follow, you know, step by step to do any of the problems that we're going to do. Yeah. It will not, right? It'll only include stuff up to like that bungee cord example. Okay, so let's say there's a ball that starts rolling up a ramp. And let's say when it first leaves the person's hand, the person who pushes it up the ramp, it's going 4 meters per second. And let's say that it goes up the ramp a total distance of 2 meters before it stops. So this is the point where it stops. And we want to know what's the acceleration. All right, well, first of all, the whole time this thing is in motion, its velocity is this way, right? We haven't chosen whether that's positive or negative yet, but we know it's going up the ramp. So what direction is the acceleration going to be if it's slowing down? It's going to be down the ramp, right? If I call up positive, then velocity is going to be positive, acceleration is going to be negative, and vice versa if I choose positive that way. And before we can describe this stuff as math, we need to make those 3 choices that we've been making. We need to choose a 0 position, a positive direction, and a time equals 0. We're actually going to have to make a 4th one now, and that's going to be the instant corresponding to that time final. Okay, basically, when do we want to turn off the stopwatch? Okay, well, let's say, let's put our 0 position here. That's the location where the ball is going 4 meters per second. And let's choose our positive direction up the ramp. And if our positive direction is up the ramp, then what's the position at the point where the ball comes to rest? Yep, positive 2 meters, because we're starting at 0 and going 2 meters in the positive direction. And then let's choose our time equals 0 instant to be at the start of this motion, or the instant when the ball is going 4 meters per second.